Okay, so just and in case like if it happens like last Tuesday that if my connection goes off, please stay there only. I will join back. Okay.
Yeah.
Yeah. So hopefully there should not be any issue. Yeah. Okay. And so what I have decided now is so semiconductor physics. If I continued now from where we left in the Uh, I'll reply to that Abhishek later. Okay. So semiconductor physics. If you see the syllabus which I had shared in the first class, the presentation file, you can see that there are a few new concepts which you have not learned before. Okay. So if I move on to that now, actually it has lots of derivations. So today, um, if I move on the first week itself, it will be difficult for you to catch it up. So what I'm going to do is, so since last Tuesday, Kavya, please mute yourself. Since last Tuesday, we have done, that means day before we have done PN junction diode and Zener diode. So I am going to continue a bit onto the diodes. So this basically is the next unit that is within the same module. I have mentioned semiconductor physics and devices for optoelectronics, right? So I'll move to the devices. We will finish the devices and then come back to the so-called derivations and a bit complicated stuffs in semiconductors. Okay. So what we learned, I'll just summarize. So the first class, obviously it was just an intro. Then on Tuesday morning, we looked into the different classification, conductors, semiconductors, and insulators. And we followed it up in the afternoon with the classification of semiconductors, that is intrinsic and extrinsic semiconductor. And then what we had, we joined these different types of extrinsic semiconductors, that is P-type and N-type, and we create a diode, a p-n junction diode. But we found that p-n junction diode has some limitations, so because of which we had to know about another diode, that was Zener diode, right? So we learned about Zener diode. So it's a Zener diode which you obviously have the experiment and all, the first experiment. Now continuing with the diodes. So I'm going to share the screen. Just a sec. Okay, it's loading. Yeah, it's come. All right. So moving on to different types of diodes, what we will do next is we will move to an LED, a light emitting diode or LED. Okay. So understand this very clearly because it's a very important thing. You'll know that what is there in LED. We all have it. We all are using it in our phones. It is there in our home. LED bulbs are there. What is so special about them, right? Correct. So LED, even though it is something being used in your daily life, it has a variety of applications. A variety of applications. You know, nowadays even the TV has become based on LEDs, correct? There are so many LEDs in that big screen or that even a small screen, whatever. There are so many LEDs together which is doing that job. Even computer monitors have become LED. And, you know, we say that having LED screens are better in comparison to LCD because LCD will be painful. Earlier we were saying LCD is better in comparison to fluorescent because fluorescent, the previous picture tube, the big TVs, that was painful for eyes, right? Correct? So we need to understand about the different diodes. All these LEDs have lots of applications in our daily life and anywhere coming into picture. You have your flashlight in your mobile as LED, correct? So many things are there. So let's understand this LED. So basically, how do I define an LED? When I ask LED, students tend to say it's a light emitting diode. But now onwards, understand it in this way. That is his first sentence. A PN junction diode which produces light or which generates light in forward bias condition. A PN junction diode. So we understood how a PN junction diode works. And it is going to work in forward bias condition. And by some method, it is going to generate light. It is going to produce light. Okay. Now, this is usually fabricated using from the periodic table elements which are belonging to group 3 and group 4. For an example, the best example is gallium and arsenic together, gallium arsenide. All right. Now, so we learned about two things last, two important things. That is majority charge carriers and minority charge carriers. P-type majority is holes, but minority is electron. In N-type majority is electron, while minority is hole, right? So there is some kind of recombine. The charges are going to recombine and produce light. So how does this happen? That is a big question. Now, okay. This effect, you also, there's a term, so don't worry much. It's also called as injection electroluminescence. Injection means what? You're injecting something, right? Whenever you take an injection, something is being done. Something is being done to you, right? Something is being done there. Electro obviously corresponds to electric field or current. Luminescence means light, right? So that is another term for it. So recombination of charge carriers or injection electroluminescence, that is another name. Okay. Now, let's understand it in this way. So you can see this figure. I'm not going to read whatever is written here. So now onwards, when you understand physics, if you have to understand figures, see some figures, see what happens in the figure. Based on that, you have to learn what really, how is this system working. Okay, so what I've done, I have considered a PN junction diode. Okay, this is N-type, this is the N-type portion, this is the P-type portion. The dotted lines, these two parallel dotted lines, it is going to take the depletion region. This is the depletion region. Okay, now let's think of this. Our previous figures, it was just like a full rectangle. You divided the rectangle into three, N-type, junction, and P-type, right? Now this looks a bit different. What has happened? I have basically considered the band diagram of this, right? I considered the band diagram. I considered the band diagram representation of a PN junction diode. So this is corresponding to the valence band. So see, N-type semiconductor, it's a semiconductor. Obviously, it has a valence band and conduction band. So N-type has a valence band and a conduction band. P-type also has valence band and conduction band. So the junction formed between them should also have a valence band and conduction band. Correct? Exactly. The same way I put another better picture here now. N-type semiconductor. This is now full rectangle kind of only. This is N-type semiconductor. Valence band, conduction band. P-type also has valence band and conduction band. And okay, for some reason, this P-type has very less free electrons in the conduction band. That is what we have, like kind of, it's not shaded here. Okay. But there is a depletion region. This is the depletion region. This vertical thing which you're seeing is the depletion region. Okay. Now in the depletion region, as I said earlier, there will be a valence band and conduction band. Okay. Now when this junction is formed in LED, so what is it so special about LED? Something it is going to do. It is a PN junction diode which is working in forward bias. That means if it's a PN junction working in forward bias, means I apply a voltage, right? Initially current will be less, and if the voltage crosses the barrier voltage, this potential barrier voltage, then what will happen? Current is being produced. Correct? That is our understanding. Current is being produced when the applied voltage crosses the barrier voltage or the knee voltage, that is a new cut-off voltage, all those terms, right? When that voltage is crossed, current is being produced. Now, when this current is produced, what happens in the case of LED? Let's see that. So here in the conduction band of the depletion region, now we are going to focus on this vertical region. Okay. When current is being produced means charge carriers are moving towards the junction. They are reaching the junction. They are reaching the junction. So here I have n types, so I have more free electrons here, right? I have majority charge carriers as electrons in n type. So some of those electrons will come towards this depletion region. So that is why this, you can see this conduction band of depletion region, I put like a, so like a small triangle it is, it's a small portion. Or basically I can say the depletion, the electrons pushed to the depletion region or the conduction band is being filled up with some electrons. Okay, it is being filled up with some electrons. Similarly, it's not just electrons which are moving, but there are holes also which are moving. So here below in the valence band also you have holes. So within the depletion region, there is a conduction band and valence band. And when your applied voltage crosses the knee voltage, current starts flowing. That means some electron, some free electron reaches to this edge of the conduction band where in the depletion region. And there are some holes here in the valence band of the depletion region. Okay. Now, some of these will be directly above, like some free electrons will be directly above the holes. Okay. Now, what is going to happen in LED? These electrons are going to, some of these electrons are going to jump below, they are going to jump below towards the hole. They feel so attractive, they find holes so attractive, so they jump towards the holes. The electrons within the conduction band of the depletion region jump towards the holes within the valence band of the depletion region. So when this jumping is happening, say suppose you jump from a height, say when you were a kid, you would have climbed on a table and tried jumping up, jumping from there, correct? Or on a maybe a teapot or something. So when you jump, you are basically, you have to release energy. You're going against a gravitational force, so you have to release energy, right? So now in the case of electrons, when electrons jump towards the hole in the valence band, okay, they have to release some energy. So the electrons jump, release energy, and that energy released is in the form of photons or light. What have I put here? I have put two wiggly lines and written H nu. H nu represents what? Energy of photon, right? Energy of photons. E is equal to H nu. This you would have heard. It's HF. Instead of nu, you would have heard F, maybe frequency. Planck's constant into frequency. That is the energy of the photon. So when what happens in LED? It's a PN junction diode which is working in forward bias condition, right? When the applied voltage exceeds the barrier voltage or the knee voltage, current starts flowing. At that moment, some free electrons, a very few free electrons in the conduction band within the depletion region jump towards the holes in the valence band of the depletion region. Okay. When this jumping happening, they have to release some energy. The electrons have to release energy. That energy being released is in the form of photons or light. Okay. And when they have jumped towards holes, they obviously come and combine with them, or you call it as recombinations. Charge carriers combine. It's a kind of nullification. Okay. So this is the recombination process. Okay. Fine. So that's how LED works. Any doubt?
Ma'am, doubt, ma'am.
Yeah.
Ma'am, in the conduction band of the depletion region, ma'am, how will the electrons first come and occupy there? From which
Yes, no, that's what I'm saying. If you understand a PN junction diode, you just take a PN junction diode working in forward bias. What did we say last week? What did we say last time? Your applied voltage increases the potential barrier, right? It has to exceed the potential barrier voltage or the knee voltage, correct? Then charge carriers will move from the N type and P type towards the depletion region. Correct? No? Correct. So it's the same process, the same thing. It's exactly the same thing which is happening. They are coming towards the depletion region. Say there are free electrons from N type and there are some holes in the P type. These fellows have come towards the depletion region. Only thing is when they reach Oh, no, Abhishek, you are misunderstanding. It's not that. See, there is a conduction band. See, I'll just repeat what I said. I have an N-type semiconductor. I take one N-type semiconductor. I know the N-type semiconductor has a valence band and conduction band. I take a P-type semiconductor, which has a valence band and conduction band. I join this P-type and N-type. What happens? Obviously, it produces depletion region. So the depletion region also has valence band and conduction band. This is just a distribution. This is the distribution. Okay. P-type, the junction, the PN junction also has depletion, the depletion region also has connection band and valence band. Okay. The bands are there. But when your applied voltage is below the knee voltage, there are no charge carriers. There are no charge carriers. It's only ions here in the depletion region. Do you accept that? When voltage is less? Correct now?
Yes, ma'am.
Okay. So now what we are saying is when you are in your applied voltage exceeds the knee voltage, that is when the current starts increasing. Correct? Current start increasing means what? The charge carriers have to come towards the depletion region. It has to come to the depletion region. Correct? When the charge carriers come to the depletion region, what I am saying now is you get free electrons. The free electrons or the electrons, you had more free electrons here in N-type. Those electrons, N-type means more electrons, right? More free electrons. Those free electrons will come to the edge of the conduction band in the depletion region. The depletion region also has a conduction band and valence band. So free electrons reach the conduction band and holes reach the valence band. Is
Ma'am,
this
then why
no?
does this process doesn't happen in PN junction diaphragm?
Wait. I'll come to it. I'll come to it in the next slide, why it doesn't happen. Okay. Now, is this point clear? You have more, you will get electrons, you'll get more electrons in conduction band and more holes in valence band. Is that clear? Is that acceptable?
Yes,
That is
ma'am.
acceptable, right? By default, you have more free electrons in conduction band and more holes in the valence band. So is that, or Fermi level, I'll come, yes, Fermi level, in a PN junction, I'll come to it later, Abhishek. It gets complicated, it becomes more complicated. So I will not come to Fermi level now. Okay. So they reach here, the electrons reach in the conduction band and holes reach in the valence band. But the only thing is this entire process happens in the depletion region. Okay. Electrons jump towards the holes, recombine, but when they are jumping, they have to release energy, and that energy releases in the form of photons or light. Now coming to the other question on why it doesn't happen in regular diode, here comes a reason. One second. Okay. What you're seeing here is the structure of the LED. Okay. Don't see what I have written here. So this is how the LED structure basically is. So you have substrate means something which stays at the bottom. So I had taken one N-type semiconductor. Over that, I have put a P-type semiconductor. So this line is actually representing the junction. Okay. This is your PN. Suppose there are no other things, there will be a PN junction. This is just a PN junction there, correct? Now, what is going to happen in the case of LED? I don't know if you have noticed, there is a outer layer glass. Have you noticed? Yes or no?
Yes, ma'am.
So there is an outer layer, right? There is an outer layer. I can come to it. I think, yeah, it is here. See, this outer layer, it is here, right? This outer layer. So what is going to happen is whatever light is being produced in the case of LED, that can go out through that. It can go out in this, between this gap. It happens here. Okay, this from the outer layer, that outer layer is a big point. So there is a substance called as dielectric here. What is a dielectric? Do you know about dielectric? Have you heard of dielectrics? Capacitors, dielectrics? Yes, dielectrics. So there is a dielectric and there are some obviously connections for taking out the current, for the current to be produced and all those things. Okay. All these connections here, that outer layer, the glass envelope, all those outer layers, everything, they all are going to help the light to come out. See, where is actually the light is being produced, where the light is being produced in the depletion region, right? When the electrons jump to the holes. So the light produced has to go out. There has to be a way. So that way is being helped by all the structure, outside structure. Okay. And one more thing I'll tell you. I'll ask you this. I have written it here. So what happens is, this is a material. This entire thing is a material, right? And outside is what? It's another medium, right? It's air. It's air here, correct? So from the material, the light being produced has to go out. So that means there is a change in the medium, and it does total internal reflection. Can you tell me what is total internal reflection? How do you understand total internal reflection? When light is traveling from,
denser medium to optic.
yeah, denser to rarer,
Mirror medium.
yeah, denser to rarer medium, the light will undergo multiple reflection, right? Multiple
Reflection.
reflection. And at the
Yes,
end,
ma'am.
the light comes out of, right? And you get an intense light which goes out. Yeah, correct. More than the critical angle. Yes, all those conditions come. Correct, exactly. So the light goes out. So LED, it's unlike the other diode. So you're seeing Zener diode. Zener diode was not producing any light in the forward bias, right? We didn't see any light in that demo. So Zener diode outer structure is different, but LED structure is different. It is made in such a way that whatever light is being produced can go out. This recombination process happens only in the case of LED. Recombination and producing light happens only in the case of LEDs. So this is a general representation of the LED. So it's a PN junction diode. I have drawn a diode triangle with a bar. So this triangle base corresponds to P type and this line corresponds to N type, correct? And this is PN junction diode. I put two arrows outward, or I can put two wiggly lines like earlier I had put, no, these two lines I can put. That is how LED is represented. The arrows pointing outward from the junction should be from the junction. This is the junction point. So arrows pointing out from the junction will be LED representation. Okay. Now, okay, don't worry about all these things. This I just put, okay. And I put, whenever I connect the LED to a supply, I need obviously a resistance to limit the flow, correct? When any electronic circuit you do, you obviously need a resistance to limit the flow of the current, correct? Okay, so a few applications, you know the application, most of them you know wherever you use calculators or wherever display and all those things, right? Even railway station, you have the display of train number, all those coach numbers, everything. And nowadays, everywhere it has become so widely used. Now, so LED was a PN junction diode. Just remember this. LED was a PN junction diode working in forward bias condition, and you applied voltage, and the current flowing through resulted into electron hole recombination within the depletion region, producing light. It produced light. Next is a device which takes light and produces current. That's known as a photodiode. So now it's a PN junction diode working in reverse bias condition. Obviously, you will ask me one question. Does not breakdown happen? No, it doesn't. Read this. They are specially designed to operate in reverse bias condition. So basically, the current produced will be very, very less. Okay, it will be in microamps. It will be very, very less current. So they are specially designed to operate in reverse bias. So by controlling the amount of doping and all, they have been designed. So photodiodes are PN junction diode working in reverse bias condition, takes light, okay, takes light and produces current. A simple definition. A photodiode is a PN junction diode working in reverse bias condition, takes light and produces current or generates electric current. Okay. Now, can you tell me why do I need light? Can't I be happy by just, I just apply a voltage across this and be happy with that current which is coming out? Why do I need light? Can anybody think? See, I've written in the last sentence, in photodiodes, both voltage and light are used as energy source to generate electric current. I'm applying a voltage. In addition, I'm using light. Can't I be happy with the applied voltage and be happy with whatever current I'm getting? Why it is not sufficient?
It is insufficient, ma'am. The amount of voltage produced, like supplied,
Amount of no, it's
voltage
not
supplied.
no voltage. It's not about voltage supplied. My voltage supplied is fixed, whether it is 1 volt or 2 volt or 3 volt. In
Yeah,
addition,
ma'am, that
I'm
is
having
insufficient for produce, like for the process to happen.
what process to happen?
That taking the light and even applying the voltage.
No. Wait, I am asking you if I just apply the voltage. If I just apply voltage, instead I don't use light.
Ma'am, because the depletion region is more,
Depletion region is more, so
the current won't pass. Like free electrons won't pass through.
can you put it in a better way? Another way? The current produced will be less, minimum. Yes, Vaishnav, the applications are correct. Current produced will be very less. If I use just the voltage, I already told you, right? Current produced will be very less. It's of the order of nanoampere and all. So that current produced is insufficient for any kind of application. I obviously, like he has already written, solar panels and electromagnetic detecting devices. If I want to use a diode for an application, if it gives me very less current, what I will do? It's of no use, right? So just voltage is not sufficient. So I need light in addition to it. So here it requires a small number of minority carriers are generated when you apply a reverse bias voltage. This is working in reverse bias. So there's a minority charge carriers which are now playing the role, not the majority charge carriers. Okay. That number of minority charge carriers produced will be very less. Now there is another problem. These fellows, so I get minority charge carriers as holes on N side and electrons on P side. They within the junction they can come and recombine. So the number of current charges in the junction will be less, or the current produced will be less. So current flow is very less. Okay. So you need to apply an external energy in order to increase more number of, or in order to get more number of charge carriers, or in order to get more amount of current. Now, this is how I'm going to represent the band diagram of a PN junction photodiode. Again, once like earlier, only thing is in LED, I had put N type on left side and P type was on right side. Now I have taken P type on left side and N type on right side. Okay. And once again, the same concept. A P type semiconductor has valence band and conduction band. N type semiconductor has valence band and conduction band. When I join them together and form a junction, obviously they also will have valence band and conduction band, right? Now, you're letting light to fall on it. There is obviously, you are connecting it to a supply also. The only thing is when you connect to the supply, the current produced is very less. Now, in addition, your light is coming. So the light is, listen carefully, the light is going to fall where? It is going to fall in the depletion region directly. It is, the photodiode is in such a way that the light produced falls exactly in the depletion region. It falls in the depletion region. Okay, it falls in the depletion region. Now, where does it fall in the depletion region? It goes directly to the valence band of the depletion region. It comes here. It comes here. Okay, light falls onto the valence band of the depletion region, and initially you were having valence electrons here, or those valence electrons absorb energy from the light which has come and go to the conduction band. They gain energy, go to conduction band and become free electrons. But an absence of a valence electron produces hole. I'm just going to repeat this. In a photodiode, within the depletion region, the light is going to fall. It falls directly onto the valence band, and that light is being absorbed by the valence electrons in this valence band, and valence electrons will gain energy from that light. It absorbs the light, right? So it absorbs. How it fall? How does it fall? Why it cannot fall? I told you earlier itself. We design it. The structure is in such a way that it can take the light. All other your p-n junction, regular p-n junction diode, the structure is in a way that it doesn't take light or it doesn't produce light. For manufacturing LED or for manufacturing photodiode, the materials are in such a way, the outer structures are able to, either in case of LED it produces light, in case of photodiode it takes the light. It's all about the outer structure. The outer structure, how is the structure? What are the materials you are using? Especially the materials you are using in producing the photodiode. Not every silicon semiconductor can make a photodiode. So LED, we gave you an example of gallium arsenide. Similarly, here I will give you some examples. Okay. Now, light falls onto the valence band of the depletion region. Valence electrons absorb that light energy and they gain energy from the light, so they go to the energy has been increased, so they go towards the conduction band and become free electrons. But when a valence electron leaves the valence band, it leaves a hole, it produces a hole, the absence produces a hole. So basically, when this light has fallen on the valence band in the depletion region, you have produced new electrons and in the conduction band and new holes in the valence band. It has resulted into electrons and holes. You get a pair at one, for one situation, I can say there is a pair of electrons and holes. There is a pair being produced. Okay. Now, what happens next? So many pairs are there. All these pairs, you have applied a potential across it. They can move. Let me come to it. I have the structure now finally like this. I have applied a reverse potential here. Light has fallen onto the depletion region. Wherever it has fallen, depletion region, valence band it comes. The valence electrons gain energy, go to conduction band, become free electrons, but they have left a hole there. So these new pairs of electrons and holes, because of your applied supply, they will go to the respective terminals. They will go to the respective terminals. Okay. And when they go towards the respective terminals, that means there is a flow of electrons and holes. So there's a flow of electrons and holes. So here, this is a reverse bias. So these orange ones are the electrons. So those fellows can come to the positive terminal, and these are the holes. They will come towards the negative terminal. When they do like this, current is being produced. Okay. Now, you would have heard of photoelectric effect. Photoelectric effect, what happens? Light falls onto a metal surface and produces current. Is this not something similar to it? The only thing is this is not a metal now, it's a p-n junction diode, a specially designed p-n junction diode, a specially manufactured p-n junction diode, which takes light and produces current. Okay, but there is a condition here. There is a condition here. What is the condition? You know that there is a band gap energy between the valence band and the conduction band, right? P-type, this is your P-type, sorry. So between the P-type, there is a band gap energy. This is N-type also, there is a band gap energy. So similarly here, you have a valence band and conduction band. So there is a band gap energy, right? The difference between them. So when this valence electron here absorbs the light, okay, so that light energy which it is absorbing, or the energy which it is gaining, should be more than the band gap energy. So suppose band gap is like 5 electron volt, and sorry, not 5 will be too much. Okay, say 3 electron volt. Suppose band gap is around 3 electron volt, and applied energy is only 1 electron volt, or the light coming in produces only 1 electron volt, then that 1 electron volt is not sufficient for this electron to, valence electron to go to the conduction band. So if it is 3 electron volt band gap, the applied light energy should be more than 3 electron volt. That means energy of the photon should be more than the band gap energy of the depletion region. Okay. Now, okay, I've written another way, I just mentioned in terms of wavelength also. That's not a big deal. So you have to just write frequency as velocity of light divided by wavelength. So you can rewrite this expression. Okay. Now, so that's about a p-n junction photodiode. A similar variety. So here you had a p-type and n-type. The depletion region was formed when you joined this p-type and n-type. Now, A similar variety is a PIN photodiode or a PIN photodiode. What is this I then? You have P type, you have N type, okay, and you have an intrinsic semiconductor in between, So that intrinsic semiconductor is going to act as the depletion region. Earlier you had only, I go back to this one, only P type, N type, they join together, produce their own depletion region. But now, instead of that one, I have an intrinsic semiconductor here. There is an intrinsic semiconductor. So it is now, see, when I have an intrinsic semiconductor on an external material, I can control the size, right? I can have more area. So now that intrinsic semiconductor is going to work like a depletion region. So when light falls, it falls onto this intrinsic semiconductor region. This in-between region is now an intrinsic semiconductor. Light falls here, same process repeats. It's again a semiconductor, so there is a valence band conduction band. Light falls onto the valence band. Valence electrons gain energy from the light. If the energy of the light is more than the band gap energy, valence electrons go towards the conduction band, become free electrons, right? But at the same time, they produce holes here in the valence band. It's the same process, it's exactly similar process. What is the benefit here? There is a big depletion region, you have more depletion region. So basically there is more area for the light to fall, or there is more chance for more charge carriers to be produced, more current to be produced. You can produce more current in the case of a PIN photodiode. Okay. Now there is one more photodiode which is called as Avalanche Photodiode. What will be happening here in case of avalanche? So we told about avalanche in the previous class, right? So what was avalanche happening? Charge carriers go and hit some ions and they produce new charge carriers. Those new fellows will go and hit other ions and then they again produce new charge carriers. Those fellows again go and hit ions, they again produce. So a more amount of current is being produced. So when in a similar way, you can produce more current in the avalanche photodiode. Exactly the same process. Your voltage applied is a bit more, and this avalanche can happen. One electron going in hit other ions, produce other more charge carriers. Those fellows go in hit other ions, produce more charge carriers, like that. So more current can be produced in an avalanche photodiode.
Ma'am, one doubt, ma'am. Ma'am, this avalanche will always happen only for minority carriers, ma'am.
Yes, exactly. Because this is working in reverse bias condition. This avalanche happens only in reverse bias condition. So the so-called breakdown in normal PN junction diode also is in reverse bias. This photodiode, a specially designed photodiode without a breakdown. This avalanche, when it happens in this photodiode, it is without the breakdown. It is in a controlled manner. Like when you ask how it happens in that one, how it doesn't happen in this one, it all depends on the material which is being used to manufacture these diodes. So here it is in a controlled manner. So the element used are different, so it is in a very controlled manner. So the avalanche will produce more current, but there is no breakdown, no chance of breakdown. Now I just missed one slide here. Okay. So here's the thing. When you initially we taught this condition, when you had only applied voltage, you didn't apply any light, right? So that current produced is very less. When you applied only voltage, current produced is less. Okay. You call that as dark current. Why? Because there is no light there. The small electric current produced under the absence of light, but due to just the applied voltage in a photodiode is known as dark current. Okay. And I'll just go back to that first slide. Where is it? Here it is. The current produced or the charge carrier produced now, see, I have written as photo-generated electron and photo-generated holes. All the new fellows are now photo-generated. They are generated due to the photons of the light. So this current produced due to light, I will call as photo current. So the total current in a photodiode is a sum of dark current and the photocurrent. So total current, here it is. It's a sum of the dark current and the photocurrent. Okay. But Obviously, if you, that means your more current is being produced due to the photocurrent, that is the photocurrent or due to the light. So you should have minimum dark current. That means minimum current produced due to just the applied voltage. So you will say your device has better sensitivity to produce current whenever you apply light. Okay. All right. It's 9:55. Now I notice that students started leaving. So, okay, somebody asked me for the application. Where is the application? Here it goes. So the different materials used are here. So other than silicon germanium, why silicon germanium? Because in a PIN photodiode, you have an intrinsic semiconductor in between. That is why silicon germanium. But other than that, in general, photodiode is manufactured using these materials: gallium phosphide, indium gallium arsenic, and this is antimony. SB is what? Does anybody remember?
Antimony.
Bismuth.
It's not bismuth. I know
Antimony.
it's
Antimony.
antimony, right?
Antimony.
Yeah. Okay. Fine.
Antimony,
So,
ma'am.
yeah. So today we will stop here. So Abhishek had initially asked me, am I recording? I am recording it for a reason that this is just the first week. So we might have, you people might have to revisit. So I will later share it by some means. And there is also a possibility that, maybe a few students will join from the second round. So for them also it is required. So that reason I am recording it. Okay.
Ma'am, for internals, you'll give this
Will you
slides
give
as well in
question
notes, ma'am.
bank, ma'am?
What? You reached the exam now itself?
No, ma'am, just
The
asking,
day,
ma'am.
the dates itself are not decided. I will give you these slides. I will give you these slides. There is an another PDF note. So I will upload all those things in the classroom today. Okay.
Okay, ma'am. And should we write down that notes or just refer it, ma'am?
You don't have to write. See, it's your way of studying. If you feel that by reading online or reading on your PDF, you can study, then you don't have to make your own notes. It is your wish on how you want to study it.
Yeah, ma'am.
Okay. Okay. I need to stop this.
Will you send question bank?
No, there will not be any question bank. We don't give question bank. We don't give question bank. Sorry. Physics, no question bank. Because there isn't anything, there is no big deal in studying physics. Engineering physics is a very easy topic if you focus. So please study. So now you can leave your maths. I think, what is the next class? Maths or what is it?
Maths, ma'am. Maths.
Okay, bye. Okay, you can leave now. Okay, bye.
Thank you, ma'am.
Thank you.
Yeah.
Thank you, ma'am.
Hmm.